So let's talk about the modes that Ext3 provides. So Ext3 provides, the first mode is journaled data. The idea is that we're going to put into the journal both the metadata and the content of the file blocks. Okay? So the content of the directories are part of the metadata, right? The directories themselves. But the files themselves, if we have a file like standardao.h, the contents of that file is one of the file content blocks. Both of those are going to be logged. So log metadata blocks, and we also log the file content blocks. Right, so that's the plan. So what are we going to have? We're going to have on disk, we're going to have the file system, and then we're going to also have a circular log. In memory, we're going to have a block cache, and then we're also going to keep track of transaction information. We're going to keep a set of block numbers, and these are the block numbers. They're going to actually have to be written back. We also keep track, in addition to the set of block numbers, the open system calls. That is, the system calls that are in progress, that are a part of this transaction. And then we're going to, what's the log look like? The log actually looks like, right, it's circular, and we have one super block. This super block contains the offset to the beginning of the log. And it also contains the earliest sequence number. So every one of our transactions, we're going to give a sequence number that is monotonic increasing. Within the log, and again, this is a circular log, so the log offset points somewhere in here, to the beginning. Within the log, we have a sequence of different kinds of blocks. So we'll have a descriptor block. We have one or more data blocks. And then we end with a commit block. What do these look like? Well, the descriptor block and the commit block both have a sequence number. So this will include what is the sequence number of this transaction. So if we have a particular sequence here, then we'd have another descriptor block after this, some data blocks and a commit block, and that sequence number would be one more than this sequence number. So the descriptor block, we have in it the sequence number. We have, for each of the data blocks in here, an entry that says where on disk do they belong, right? So this is just the contents of the data. That's all the data block is. So the contents of data that needs to go somewhere on disk, contents of data needs to go somewhere on disk, and so on. And so this will just be the block numbers for each data block. The other thing we have here is, at the beginning, a magic number. So this magic number is used to ensure that we can recognize a descriptor block or a commit block. So the commit block also has a magic number. I think it's the same number, although I'm not entirely sure. And it also has a sequence number. Okay, it has no need, which is a match to this. So the sequence numbers match. So this magic number is going to allow us later on, if we need to be able to go through these blocks, in case we had some crash, go through these blocks and figure out which ones are descriptor blocks and which ones are data blocks. And the magic number will tell us. You might say, how will that magic number actually work? Because what if this data block happened to have that magic number at that same offset? And the answer is, if a particular data block does have that magic number at that offset, then we go ahead and zero it out in that data block and make a little mark here. So we mark if it had the magic number. And if it did have the magic number, so we're guaranteed within the log, none of these data blocks will have the magic number. But if we go back and look at the descriptor block, it may say, hey, this data block actually did have the magic number when it initially came in. And therefore, before we actually write it to the file system, we will go ahead and set its magic number back. The transaction can handle multiple system calls. Okay, so it's not unlike Ext3 in that way. We have this batching where we will just open up a transaction and then allow system calls to happen until we either run out of potential space in the log or until a timer goes off that says, let's go ahead and close that transaction. What are the advantages of that? Well, one advantage is we're amortizing some fixed costs. So for instance, the descriptor block and the commit block are fixed costs for a transaction. The more data blocks we have, the less overall cost those have. The second advantage is write absorption. You can imagine we've got a block in the cache that's part of a transaction. So some system call has modified it. Let's say it's a directory and someone has created a file in that directory. Okay, so that block has been modified, and now some other system call goes through and also does something in that directory that requires a modification. Then it can just modify this block in the cache. So rather than having multiple blocks in the log, instead we're going to have a single block in the log, and we'll have what's called write absorption, where multiple writes to the same block turn into actually just one write to disk. One thing to note is that when a particular system call returns, the blocks may not have been written to the disk. And so they'll be written soon. Once this transaction finishes, then as part of the committing, it'll be written to the log. But until then, it won't. That can be a problem. For instance, let's say you are writing a mail server, so an SMTP server that someone else connects to send mail to this machine. Well, when the mail server returns okay, the other side is going to throw away that mail because they know that that mail made it to its destination. Well, if the mail server, when it gets a message, writes it to disk and then assumes that's and then responds okay, then if the machine crashes at that point, there's a problem because that mail doesn't exist anymore. The original sender passed it off to the mail server because the mail server said it had it. But the mail server actually didn't make it to disk. So there are ways in which you can actually what's called sync a file and then just cause it to go to disk. These transactions, so we can have multiple transactions. So let's look at the state of these transactions. So we can have multiple committed transactions in the journal. Or a journal and log are really the same thing. Okay, we can have multiple transactions that are committing. However, they have to be in order. Actually, one of them is committing and the others are waiting. The next transaction in age will get to commit, and then the next get to commit, and so on. We have one transaction that's accepting system calls. So this is what's called an open transaction. That's the one when a system call comes along that the system call is likely going to be, file system activity will be into that open transaction. Unlike Ext3, so in Ext3, once you closed a transaction, you had to wait for it to fully commit before new system calls could run. And that's not the case. When a transaction closes and it begins the commit process, it's going to just get in line with these other transactions that are committing, and we'll just open up another transaction. So the level of concurrency is much higher in Ext3. Let's look at a sample system call. So this is a system call that deals with the file system. And what's it going to do? Well, the first thing it does is it calls start. Okay, so start is going to add this system call to the open transaction and return what's called a handle. Then, via the handle, it can get a block. This is going to return a block in the block cache. It may be necessary to go to disk to get that block. It can then modify block, and then when it's done, it calls stop. And it may be a whole lot of getting and modifying, right? If we imagine writing to a file, there may be many blocks that actually get gotten, allocated, written to, and so on. So we may be writing to an inode, we may be writing to an indirect block, we may be writing to a file system block, and so on. When we do start, so start basically says to start making writes atomic. And the stop, of course, ends the atomic portion. And these are all then being handled in the open transaction. So the open transactions knows which open system calls there are. By open system calls, I mean the ones that are currently in progress. And it can't actually finish the transaction until all of the currently in progress transactions finish. So it's going to keep track basically of how many stops there are in comparison to the number of starts and make sure that all have finished. Start may block. Why might it block? Well, there are two basic reasons it might block. One reason it might block is that the decision has been made by the file system that this transaction is ready to go. Okay, maybe it's been enough time. It's been 15 seconds since the last transaction, and so it's going to go ahead and close off any new system calls into this transaction. That's one possibility. Okay? And so that will basically just wait for the current system calls to finish and then start committing this transaction and open up a new transaction. Another reason is maybe there's not enough space. Maybe it looks at the set of block numbers and the number of system calls and realizes there's not going to be enough space if we allow another system call. Okay, how does it know that? Because actually when you start, you have to give it an upper bound on how many blocks you are going to be writing. So in Ext3 we just said there's a single constant. No system call should take more than this number of blocks. Here, we actually let the system call decide. So the system call is going to say in its call to start how many it's going to need. The get operation is going to actually add, so it'll retrieve a block number. The block may already be in the cache. The block may already be in the transaction, in which case it just needs to return it. But if it's not in the transaction, it will need to add it to the set of block numbers so that we know this transaction covers this particular block. So for example, we may get this block. If we get this block, let's say this is number 199, then we'll go to add 199 to our list here. And then stop is, again, you're going to just keep track of how many open system calls there are. If all of the system calls have finished, right? If this is a stop that says, okay, there are no more open ones, then the transaction may commit, although it need not, right? It can, so it may want to continue and allow more system calls. Maybe it's just been a quarter of a second since the last time we had a transaction that committed, and so we're going to just wait for more stuff. So what are we going to do on a commit? The first thing we're going to do is block new system calls. Okay, we don't want any new system calls to move forward. So they're going to just sit in their start and wait. And when I say new system calls, what I really mean is new system calls that are using the file system. So it's when a system call calls start that it will be blocked. And then we wait for the in-progress system calls. Okay, so we check how many system calls are open, and we make sure we get back down to 0. At that point, we can go ahead and start a new transaction. We can open a new transaction, and we can unblock the system calls from step 1. So now they can start going into a brand new transaction. What do we need to do now? Well, assuming that all the previous transactions have finished committing, then we can go ahead and first write our descriptor block. So we'll write our descriptor block with our set of block numbers. We will, what else goes in this the descriptor block? A sequence number, the magic number. We also check all the blocks that we're going to be writing and making sure that there's no magic number in them. If there is, we'll zero that out and we'll go ahead and mark it in the descriptor block. Then we write all the blocks that are in the transaction to the log. So they're all going on. So we wrote the descriptor, data, 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 data. That's fine. So what do we do next? We wait for all the writes to complete. Why? Because we want to make sure that once we've written the commit block, that everything else is already there. So we want to make sure that the descriptor block that we've already asked to be written and all the data blocks that we've already asked to be written are already there before we actually take the commit step of writing the commit block. So we write the commit block, and then we wait for the commit write to finish. At this point, we're now committed. We've written the commit block, we know it's there, our journal's there. Now we do something very different from Ext3. We don't say, okay, we're going to go ahead now and write those data blocks from the journal to the file system. Instead, we say, well, we have got these blocks. Let's say it's this block in the file system and this block in the file system, and perhaps we have another block in the file system. These are all part of transactions. However, they're now transactions that are committed. And committed transactions, the associated blocks, can be written back to the file system and should be written back to the file system. So we don't force it. We just, eventually, we know everything in the block cache. If it's dirty, eventually goes back to the file system. These are all dirty. Otherwise, they wouldn't have been part of a transaction. And they're all committed now, so they're allowed to go back. So the rule is no block associated with a transaction can be written to the file system until it's committed. And the reason for that, of course, is that if a crash happens, we can always replay these. But if it's an uncommitted transaction and we've written a block back, the remaining blocks in the transaction aren't guaranteed, so we don't have that atomic behavior that we'd like. Let's look at a scenario. Let's say we have two system calls, or two processes, let's say. One does a remove on a file. The second creates a file. And let's say that this inode is actually reused. So the inode that X removes, so assume that this is the last hard link, that gets freed, and then B goes ahead and reallocates it. Is there any way that a crash would reveal some sort of an anomaly? So is it possible that B could somehow commit first before A? And so then we'd have this problem that they're both using the same inode. Well, let's look at the possibilities. Possibility one, A and B are in the same transaction. If they're in the same transaction, then that means that the inode that was freed and the inode that was then reallocated are happening together, and they're happening atomically. So that's okay. Either both of them are going to happen or neither of them are going to happen. Okay, let's look at another possibility. So A is in T1 and B is in T2. That is some later transaction. Well, in that case, when the transactions commit in order, so it's not possible for B to commit before A. So A commits as part of transaction 1, and then that inode shows as free, and then B commits and reuses that inode. Is it possible that B could be in some earlier transaction? So let's say somehow that in T1 we have B occurring. And then in T2 we have A occurring. And I'm showing some sort of overlap because the system calls can overlap even though they're in different transactions. But the fact is the starts and stops can't overlap, right? So the stop of B has to be before the start of A. For that reason, B can't ever see A's free of the inode, right? B is going to have to be allocating some new inode that is not the inode that A is free. And the reason for that, right, is we don't start any system calls in a new transaction until all the system calls in the previous transaction have stopped, that is, have finished using the file system. So this is not a problem, right, in cases 1, 2, or 3. Let's look at a particular problem that could occur and what the mitigation for this is. So let's say we have transaction 1, and transaction 1 has a system call that is going ahead and modifying this block. So this is block 37, and it's part of transaction 1. Now, so we make some changes here, right? We, it says hello. All right, so T1 modifies 37, and now we're committing. T2 comes along. It starts here, and it also modifies 37. That's certainly a possibility. It's an individual, it's a separate transaction, and it's allowed to modify any blocks at once. Let's say T2, its modification is it writes, so this writes hello, and this writes something else. Writes something in, I don't know, blue, writes XX. The problem is, if T1 is now writing this block to the log, it's going to now have a log entry that says not just hello from T1, but also part of T2, right? Because T2 is writing an XX. So we have a block that is part of T1, but also has part of T2 stuff in it. So what's the solution to this? Well, the solution is transaction transactions write blocks as they exist at the time the commit starts. So they write not what they might have been after the commit starts, but only what they were at the time. So think of it as sort of taking a snapshot. You do the commit, we have the transaction that has all the list of blocks. We're going to conceptually copy all of those blocks, and that's what we're going to be writing to the log. That is potentially expensive. So how do I actually implement that? We actually implement that using copy on write. So we give T1 a copy of 37 as it existed when T1 closed. And the way we do it is you use copy and write. So what we actually do, so we'll go back, we do the close, okay? We mark this in some way, right? We're marking that this is part of T1, and we're still committing. And now, when T2 does a get on the block and tries to get block 37, we look and say, okay, 37, that's fine. But wait a second. 37 is in the list of blocks of a transaction that is still committing. Since that's the case, we actually need to make a copy. So we are going to go ahead and make a copy of this block. And it's going to still marked as 37. And it's still going to say hello. And this is the block. Well, which one? It doesn't matter. One block gets sent back to T2, and the other block is now just private to T1. So a get is never going to return this anymore. A get will only return this one. So that way, when T1 finally gets around as part of the commit process to writing this block to the log, it's going to be writing the version that we had at the time it started the commit. So one really has to kind of be careful in this trade-off between speed versus accuracy. And Ext3 really has to do some tricks to make sure that we get as much concurrency as possible. Let's see what happens as far as how the recovery actually works. First off, when do we ever free any of these transactions? Right? So we've got one process that's kind of closing transactions, committing, writing them to here. We must have something else that's freeing them. And the freeing process happens basically, we look at this transaction and we say, have all the data blocks been written to disk? So if all the data blocks have been written to disk, and I should be clear, what I really mean is written to the file system, then we can clear this transaction. And what does clearing the transaction mean? Well, that would really mean updating the superblock, changing the offset to point to the next value, and changing the sequence number to point to the next sequence number. Let's look at the performance of this a little bit. If we just do an rm star, and we take a directory with 100 files in it, how long does that take? On Ext3, it takes a while, more than 10 seconds. On Ext3, it's much quicker, maybe 20 milliseconds. Why? Well, because in rm star, what we have is a bunch of unlinks. Each unlink is going to turn into its own transaction. Okay, so we're going to end up with 6 synchronous disk writes per system call. Wow, that's expensive. In Ext3, what's going to happen? Well, what's going to happen is the rm star is going to write the same inode blocks and also the same directory entry. And so that's going to mean that we're going to end up just updating cache blocks. We don't do any writes at all until we get to the end of that. And then it's going to be just one commit of really a few metadata blocks, right? So all we need to do is update the free inodes and update the directory contents. So it's possible this is going to be spanning multiple blocks, but not a lot of blocks. And this is probably not going to be many blocks either. And then how long does a commit take? The commit itself is very quick, right? The commit, we just need to log the descriptor block, log these data blocks of just these ones, and then go ahead and put a commit block. That can be done in about 2 rotations. So we can have 1 rotation of the disk to do the descriptor and all the data blocks. We wait, we make sure it's all written, and then do 1 more to do the commit. So about 2 rotations, about 20 milliseconds. Let's look at what happens on a crash. Let's look at the log, for instance. So the log may contain some complete transactions. So we might have, conceptually, let's say, T1, and we might have T2, and we might also have T3. And then let's say we have half of T4. Why do I say half? Because there's no commit record there. What's the superblock going to be pointing to? The superblock is going to be pointing to here. Let's go ahead and put in some sequence numbers. So I'll call this one 5, 6, and I'm going to write a sequence number at the beginning and the ending. So the sequence number for the descriptor block and a sequence number for the commit block. Descriptor block, commit block, descriptor block, commit block, descriptor block, not the commit block because we didn't finish this one. So our goal is T1, T2, T3, it acts as if this is finished, and T4, like nothing happens. So nothing of T4 makes it. What else do we know? We do know that there's some disk blocks that were in the buffer cache, and we could have had T1, T2, or T3 disk blocks. So these are from T1, from T2. This color doesn't match, so these are actually T3. And I know that if there were any T4 ones, the T4 ones never made it to the file system. How do I know that? Because the rule is until the transaction's fully committed, none of the blocks from the buffer cache can actually be written to the file system. So what might we see on the file system? We might see, for instance, I don't know, one of the T2s and one of the T3s. Certainly there could be T1s that made it as well, but we're guaranteed there's no T4s that made it on the file system. So this is what's in the file system. This is what is in the log. The earliest sequence number should be 5. All right. What do? First, we find the start of the log. That seems simple, right? We just read the superblock and it tells us the answer. But that's not quite true, right? Because we may have actually totally finished a transaction, right? All of the data blocks were written, and we intended to write the superblock, but the superblock didn't actually write yet. Let's say that's the case, right? Let's say T1 had actually, we'd totally completed all of its blocks from the buffer cache had made it back to disk. And we had finished T1 and we were in the midst of about to write the superblock, but we didn't get to. So this is actually slightly outdated. It should really say 6 and it should point to here. But what's it going to hurt us to redo this? Nothing. We then find the end of the log. We don't have any reference to the end of the log. So how do we know where it is? Well, basically, we just start scanning. And we're scanning looking for valid transactions. So what's a valid transaction? We have the magic number of the descriptor, and then we have the magic number of the commit, and the two numbers match. And then we have adjacent to that an increasing sequence number, magic number, magic number, magic number, magic number, magic number. And then as we look here, and we keep looking, we never see a corresponding commit for number 8. So we know, this is a incomplete transaction. This is the last one. So we know we're going from 5 to 7. And then what do? We just start replaying them in order. Replay 5, replay 6, replay 7. Does it hurt that T2 already has some blocks there and T3 already have some blocks there? No, because when we run through these blocks, we're going to just rewrite those, the same exact blocks. That is how recovery works. It's fairly straightforward. What if there's just a random descriptor block in here somewhere? Or there might even be a random commit block in here, right? We just might have gotten really unlucky and we had a descriptor block, we wrote some data blocks, and then all of a sudden there happened to be an old commit block here. Well, can't be a problem because the sequence number won't match. The sequence number is going to be smaller because we're always increasing that sequence number. We also already talked about the fact that the data blocks can't appear as though they are descriptors or commits because they don't have a matching magic number.